and welcome to this manufacturing systems technology part 2 module 17. We were talking about the different control charts, and in context of that we have to plot the X chart and the R chart as illustrated earlier. So, let us actually look at some of the issues related to the ground realities associated with plotting these X bar and R charts, and I would have a checklist which needs or which talks about how at the level where the recording has to be carried out, what are the different aspects that one has to keep in mind before generating these X bar and R charts. So, it is helpful to visualize the decisions and calculations that must be made and actions that need to be taken for plotting a X and R chart. Some of the actions are given here. One is the decisions preparatory to the control charts. What are those decisions? When do you realize really that a control chart needs to be plotted? So, first of all you have to set some objectives, right. So, for example, you are monitoring a slot width of a milling of a milled product, and basically doing face milling operation and then trying to create or slot milling operation and trying to create a slot within that product. And maybe one of the observations could be, or one of the recordings that could be made in such a control chart is to see whether the particular dimension that has to be slotted is being maintained, and that could be a function of the cutter, the wear at which the cutter may sort of degrade away, or the change of dimensions resulting because of poor machining conditions, or maybe vibration and chatter. So, there is a requirement of plotting the measurements in that particular manner with the objective of measurement of the slot width of the particular milling system which is in place. So, that starts the process. You have a possible objective, I have choice of variables, probably the width here, the slot width here is the variable which is the reflective variable of the quality of the process. Then you have to have a decision on the basis of the subgroups, and basically this is really based on what is your average level of production. The subgroup size has to be chosen very carefully. Subgroups basically mean that at a throughout a production length, for example, there are let us say 1000 items which have been produced, you cannot keep on continuously measuring everything. So, you have to create small subgroups in between at various points of time during the whole running of the production shift, and you will have to keep recording this for the whole batch from time to time. And the idea is, once you have started recording something, some observation, it has to go on for at least a few numbers before you sort of stop recording on that particular event period, and then go for the next event period. So, there are different event periods like this in the whole production shift. It may be a group of 5 observations. These 5 could be, let us say, the every second or third item on the production line. So, you are basically recording every third item 5 times, let us say the subgroup size is 5, and then waiting for a few hours, and then again recording after some more hours, the same every third item 5 times again. So, this kind of a scheme can be developed, and that is really based on your practical decision making at the ground root level, where you are a supervisor and you want to really associate yourself. You have process knowledge, that what kind of variations can happen, what is the interval at which the variations would happen, and that would really lead to the determination of the subgroup size. So, there is decisions on size and frequency of these subgroups. So, after the decision on the basis of the subgroups, you have also made decisions on the size and frequency of the subgroup, and based on the basis that you have made earlier, and then you set up the forms for recording the data. In fact, I am going to show you such a form just in about the next slide, where next slide, where we can give you an organized representation of how this recording of the data can be carried out. And then obviously, you have to determine the method of measurement, whether it is related to just a vernier caliper which you are inserting in that slot for measurement, or maybe it is something to do with the gauge that you have built, which you basically align and see whether a particular gauge of a certain value is going into that slot width. So, many options like these are available. So, once this decision preparatory to the control charts have been taken, now the question is how to start the control chart plotting. So, make and record the measurements and record the other relevant data, calculate the average X bar for each of these subgroups, and the range basically means the maximum observation minus the minimum observation. So, that is the range, and so you have a R bar, you have an x double bar and you have an x bar, these three things. X bar is basically related to whatever subgroup size you have. Let us say you have 5 subgroup size, what is the mean value of that particular subgroup, and R is basically the x maximum minus x minimum in that particular subgroup. Okay. And then you have many R values of the different subgroups you have measured along the whole production shift, and you have many x bar values, and so a mean of means, that is x double bar, is basically the overall mean of the whole shift, and the different range values can accumulate together to form a range bar or R bar, which is the sort of a mean range, of the subgroup of events that you are monitoring. So this is how you are trying to make extensive observations in a relevant manner, which probably you are aligning with your thought process on the observation that you have already made. You probably are aware of the cycles as a supervisor where there may be a chance of defective, and so your subgrouping and your interval of the grouping will be based on that experiential basis, or that experiential domain knowledge. So it becomes very accurate sample based on that experience. So you have to really, as a supervisor, provide this measurement and the subgroups in a very honest and integrated manner, and you should be able to justify why you are doing a certain group size, a certain frequency of the group size in terms of the possibility of occurrence of some defects, which you may see over a large time horizon from time to time. So plotting the X and R chart is the next mission. So you have calculated the average X bars, you have calculated the range for each subgroups, and you have tried to make limits, and I am going to show this to you, how the limits are being formulated, and then once the limits are there, then you keep on plotting the X bar values for each subgroup forever, for maybe a longer time horizon, for a period of, let us say, 30 days, across the whole month, once the average has been more or less ascertained and the upper and lower control limits have been defined. So I am going to go to that step a little bit later when we talk about more the upper and lower control limits, but as of now let us look at what are the checklists. So then the other ones is determining the trial control limits. This is really a decision which is required based on the number of subgroups that you have found out before the control limits are to be calculated, and there is a procedure with which we will calculate it and show you that how these, there are standard tables which you have to refer to based on, let us say, the group size, or the group frequency, and there are various constant factors which are associated with that standard table, which will tell you about the how the control limits can be placed with respect to the mean of means, that is X double bar. Okay. And then you plot the center lines and the limits, and then the idea is that all observations that you are recording would keep on continuing to be between these two limits and the central line, and then you can give an estimation of whether the process is going towards one side of the mean, to the other side of the mean, or away from the control limits. So all these things can be judged. So if you have a continuous monitoring of the quality, this is the best basis, that whenever there is something going outside the UCL, the upper control limit or lower control limit, you can say that the process is going out of control and take a countermeasure so that it can come back to normal levels. And then you have drawing of preliminary conclusions from these charts, right. So and that also we will try to do for a particular example problem. So it can indicate either a control or a lack of control. It can indicate or interpret the processes which are in control vis-a-vis those which are out of control, where you can change the focus from in control to out of control processes. You can also have relationships between processes out of control and specification limits, which is very important for measuring process capability as such of the system. If a machine is producing some abnormal range of products with a mean which is probably off centered, and it so happens that the specifications are sort of, whatever specifications are given by the design is within the limits that are being set in for the production process. So there you may end up producing more defectives in that way. So we will have to do something so that it can control back to normalcy. So that is regarding checklist necessary for X bar and R charts. Now let us look at decisions preparatory to the control charts. You will have to have some objectives, possible objectives laid out. First of all, you have to analyze a process with a view to secure information which is to be used in changing specifications or in determining whether a given process can meet the specifications or not. So there has to be a view of that. So basically if your manufacturing process is going too out of bound, a critical economic decision has to be made, whether the machine needs to be changed or whether the design specification needs to be revised, okay, so that the process being the same, can we continue having more acceptability rate. So these are some of the management issues which are involved. So it has to be very seriously done, that is very important. Okay. So again, to secure information to be used in establishing or changing production procedures, secure information used in establishing or changing the inspection procedures or acceptance procedures. These are some of the possible objectives that could be lined up for describing the analysis process behind the control chart. Also, you have to through a control chart provide a basis for current decisions during production, so as to really the time period when you have to hunt for the causes of variation and take action, and then also check whether the action suggested has been implemented, and because of which the process comes into control again. And then obviously you have to provide a basis for the current decisions on acceptance and rejection of manufactured or purchased product, where if you are a end customer from a vendor, you can probably screen off those which are faulty as opposed to those lots which are okay. So this is again another very important aspect, which can be a possible objective for a chart or a control chart. So regarding the choice of variables, the variable chosen for control charts for X and R must be something that can be measured or expressed in numbers. It could be dimensions, it could be hardness number, some tensile strength parameter, some weight. These are all numbered quantities, as you can see. These are physical quantities which you can really measure. And from a standpoint of the possibility of reducing production costs, a candidate for a control chart is any quality characteristic that is causing rejection or rework involving substantial cost. So that decision making is really your business. You are the process owner. You are associated with the daily maintenance and production activities related to a process. So you are the best judge to really comment about what are those perennial causes. That could be done by Pareto analysis or some other analysis, as has been shown before, which would lead to the rejections and the rework. Okay. And particularly those where substantial costs are involved because of rejection and rework, those are the sort of points which you could split up into terms of measurable quantities, which you then need to control, using the control chart logic. And also from an inspection standpoint, the destructive testing always suggests an opportunity to use the control chart. That is because you don't want to destroy all the products which are being made. You have to do that on a sampled basis. Okay. And if you have like for example, ultimate yield strength of a material, you can't really get this parameter without having to destructively test the sample. So in a production process, if all the samples are measured, you are not going to have anything at the end of the day. So therefore, on a subgroup basis or on a certain frequency basis, if you could have a sample to probably which could be 1% of the whole production lot, okay, and if the subgrouping and the timing of the subgroup selection is done in an appropriate manner, this 1% should be able to give you a fair estimate of the whole population. Okay. So that is again how the choice of variable, or what are the, that is again what conditions you should sort of keep in mind while choosing the right variable associated with the control chart. So once you have this all the parameters, the question of the what basis to be followed for the subgrouping needs to be brought into picture. So but this really idea was this at the first time it was proposed by Schubert, who the key idea behind this method suggested by Schubert is the division of observations into so called rational subgroups. Okay. And the subgroup should be selected in a way that makes each subgroup as homogeneous as possible and gives the maximum opportunity for variation from one subgroup to another, and this is something which you have to really know as a supervisor. Okay. So what points of time you have to make the observation, so that you have good homogeneity during one session of subgroup collection, and the moment you change to another time domain, another subgroup, there is some variation between the subgroups. Okay. So this gives you a very good estimate of the actual health of the process. So as applied to control charts on production, this means that it is of vital importance not to lose track of the order of production, because control chart is only an assistive technology. You have to remember that the final goal is really the output of the production. Control chart can only be a subdomain information collection system which should not really jeopardize the main cause, which is really the high level of production at the particular center. And if the purpose of the control chart is to keep detecting shifts in the process average, one subgroup should consist of items produced as nearly as possible to at one time. The next subgroup should consist of all the items all produced at a single time later, and so forth, so that with time also you have good spacing, of those subgroups. Then comes the decision on size and frequency of the subgroups. Shewhart, when he did his control chart experiments, he suggested 4 as an ideal subgroup size, but in industrial users 5 seems to be a better alternative because of the ease of calculations, particularly when you are talking about a coded variable analysis, so that the computations reduce. You have just seen in the last lecture about how coded variable can be done. A multiple of 5 or 10 is always a better calculator or a easier calculator in comparison to maybe a sort of a group size like 4 or 6. So therefore 5 seems to be better, although 4 was considered to be an ideal subgroup at that time. The essential idea of the control chart is to select the subgroup in a way that gives minimum opportunity for variation within the subgroup. It is therefore desirable that the size be as small as possible of the subgroup. Subgroups of 2 or 3 may often be used to good advantage, particularly where the cost of measurements is very high, and so you can save some cost by creating a smaller subgroup size. The only thing you have to be worried about is that the subgroup size has to be representative of the population. Okay, so that's something that is really the challenge that a supervisor of a line faces who is actually doing this recording, and that's where the experiential domain knowledge comes into picture of a direct association with the process of the concerned person. So the larger subgroups of 10 or 20 are sometimes appropriate if it is desired to make the control chart sensitive to small changes, but generally the principles followed are probably a subgroup of not more than 5 or so. So based on that, now you have the size, frequency, you have all the other decision criteria like the basis of the subgrouping, the objective selections, the choice of variables. Now you are all ready to record the data. So let us look at the ideal form for recording the data. You have to display this typically at the production center where things are being continued, and there particularly when you are talking about a process related control chart. And so you can see that in one page, which you can probably display somewhere down the line in the place which is the production center, you have to measure and record it all. Okay, and for doing that, in this particular case, for example, they are measuring the width of a milling slot, as I had already told you in a this is in fact some information which has been supplied by a airliner company. They are talking about a terminal block which is actually a more of an electrical component, and there are some fictitious figures like the department number, the order number, so on and so forth, but then you can actually see how detailed description can be made in some of these representations. Okay, they have given a unit of measurement which says that it is 0.0001 inches over 0.8000 inches. That means typically what you are doing is that you have made the same coded variable analysis, you have made all these the values that you can see here are reported as 0.8 plus 0.0001 times of the value that is in question. Okay, so basically this actually represents 0.8772, this 0.8756, this also again 0.8756, something like that. So the coded variable here is really that it is 0.800 inches plus the factor which has been given 0.0001 inch times of the observation which has been recorded, and this is an easier way rather than writing a decimal place and writing the whole values. You are trying to have a coded variable into picture. So this is how you lay it out. You can see there are different subgroups here. For example, there is subgroup 1, subgroup 2, 3, 4, 5, 6. There are about close to 16 subgroups. Maybe these are spaced at certain instances of time. And you can look at the subgroup number. You can see that there are exactly 5 elements in each subgroup A to E. Okay, and the recording is taking place at different points of time. And you have a option of calculating the average by calculating total. So you have a group average which is being calculated. You have a range which is actually represented by the minimum minus the maximum minus minimum observation, and then you have the date or time of the recording. So, here for example, you have the date or time given here is 7th March. So, there are 3 subgroups done on 7th March, 3 on 8th March, 3 on 9th March. So, basically it is 3 groups every day, 3 subgroups every day of production for a period varying between 3rd March all the way to sort of 2nd of April. Okay. So, you have completed like a 1 month observation here in this particular control chart. So, having said that, now you can actually see that there is a option for X bar and R. So, all the X bars here which are reported on these particular average X bar and R range R rows have been replicated here again. 770 for example is the first average of the subgroup, and the range there is 85. So, we are reporting 85, and so this way between 1 to 16 days that the recording has or 1 to 16 subgroups that the recording has taken place, you have the various X bars and you have the various ranges. So, it is the total of all X bars and the total of all ranges. From that you can calculate the average by just dividing it by 16, the number of subgroups, and that way you can calculate what are the X double bars and R bar. That means the mean of means is basically 12, 129, the summation of all the X bars divided by 16, which comes out to be about close to 758, which is meaning to say that the mean of means has a dimension 0.8758 of in inches, and then the R bar has the range bar has turned out to be 39 in this particular case, which is a summation 621 of all these different ranges divided by the number of subgroups. So, having said that, now you have to go back to the Shewhart control method, where they really talk about the factors which are associated to plot the X chart. So, typically there are 2 control limits that have to be set. One is the upper control limit of X, another is the lower control limit of X, and I am going to share that table with you a little later along the process. But as of now, you just think of it in this manner, that based on the subgroup size that you have obtained, you can actually select the A2 value and the A3 value. As you can see here, the the A2 value basically, which is giving the upper control limit. If you plug X double bar plus A2 R bar, let us just look at this UCLX value here. You have X double bar plus A2 R bar, and you also look at LCLX value here, X double bar minus A2 R bar. It is very clear from these expressions that the UCLX bar and the LCLX bar are coming out to be corresponding to a subgroup size of 5. The A2 value is actually 1, okay, and that is given in the Shewhart's table. I am going to share that table later on. So, subgroup size 5, A2 is 1, and so the plotting happens as X double bar plus A2 R bar as the upper control limit UCLX, and X double bar minus A2 R bar as the lower control limit LCLX. So, having said that, these are how the UCLX and the LCLX bar varies, and then we will also have the UCLR, right, which is basically the upper control limit of the range chart. So, you have a chart describing the ranges, and you have a chart describing the X values or the quantitative measurements. So, here when you do a subgroup of less than 6, the Shewhart method says that for subgroup size less than 6, the D3, which is actually recording the lower control limit, is actually 0, okay. And so, above 6 there is always a lower control limit for the range which comes up into picture, and these are simply statistical observations which have been recorded as a chart out of many such control charts to see if the process is in control or out of control. And then the D4 value is here recorded as 2.11 in the Shewhart's control chart, corresponding to a subgroup size of 5, okay. So, this D4 is recorded as 2.11, and so you can have a upper control limit for the range and the lower control limit for range in this case, because the subgroup is less than 6, is equal to 0, okay. So, this is the whole control logic behind plotting the control chart. Now, you just have to draw the mean value, the upper control limit and the lower control limit, whether it is the range chart or whether it is the X double bar chart, and these two charts typically are graphically plotted in one paper, and then all you need to do is to have your subgroups of observations beyond this period. This period has been used as the basic period for calculating the control limits, but beyond this period also the production exists. So you need to just keep on plotting and extending the various mean and the range values in a similar manner. The only thing you need to change is to sort of change this record form every time from month to month, and probably between April and May you will have another form, between May and June you have another form, between the same dates as have been given. And for this period the extension of the mean and the control limit kind of goes, whereas the separate points which you are generating for each month's recording is being extended on the same line. So you can have a very quick glance over a time horizon range of 6 months or 7 months and quickly say whether a month's production is going out of limit or not, and accordingly take a countermeasure. So that is how you do the control chart, X bar and R control chart. I am going to show you the plot just a little bit later. You can actually also do this in a little different manner by saying that now you do not want to create a situation where you have a third digit of decimal, you have created a second digit of decimal. So you say that this can be represented in a coded manner as 0.800 plus 0.001 times of whatever is the value recorded. Here you are recording only 2 digits of decimal, and in the similar manner you can have a little bit lesser accurate analysis for doing the slot width measurement. Okay. So the only issue here is that there may be a slight problem in this overall strategy, that supposing if the operator forgets to look at the temperature of the particular workpiece, after a milling process is over, it is always that the workpiece is overheated, and because of which there is a linear dimensional expansion. So if supposing the operator who is recording this, if he accidentally forgets to take that into issue, there may always be an undersize, because the part would have extended along the slot and there would be always a tendency of the slot to be lesser in width. And so that issue he needs to understand. Obviously the supervisor, who is the controlling authority who has decided the subgrouping etc., has to have this overview in mind at the place where this milling slot is being produced. Okay. And so you think of it that the process is discretely divided into so many such milling, drilling, different kind of machining operations or even fitment operations, but the same logic can be used at every level of the whole production system. So having said that, I will probably like to close on today's module in the interest of time, but we will go ahead and see some of the associated issues about what is the control logic that is used to interpret something about the process so that a corrective action may be taken. So we will do that in the next module. Thank you.